Okay, so in the last video, we started to talk about plate height and factors affecting plate height. Remember, we had the longitudinal diffusion, the regular flow paths, and the mass transfer term. Each of those terms could broaden our chromatography peaks and contribute to the plate height, H, increasing. And remember, when H increases, our plate height increases, that's bad, okay? We want to minimize H, or plate height, as it's called. It's just like a statistic that chromatographers use to keep track of how well their method performs, so how narrow their peaks are. Now, remember last time at the tail end of the video, I presented essentially these equations, okay? I want to return to that real fast just to make sure we understand. To compute plate height, H, for a particular peak in a chromatogram, it's always computed for a particular peak. You will go to your chromatographic data, your chromatogram. Again, it's a plot of detector signal in time. You see your Gaussian shape peak. And what you need to do is measure two variables from this peak, okay? One is the full width at the base. And the other one is the so-called T sub R. And remember, we called that one the retention time. That is the time required for that peak to appear at the detector. It's basically this x-axis variable right here. Time required for the peak to appear at the detector, retention time. So you take your W, you plug it into the numerator of this equation, you take your retention time into the denominator. Now both of those will have time units. You need to use the identical unit, either minutes or seconds, doesn't matter which one, but they have to be the same. And then what you do is you take the ratio, you square it, multiply it by L divided by 16. Now L cannot be found from the chromatogram, because L is the length of the chromatography column itself, how long your tube is, which is packed with your stationary phase. You're going to need to know that if you're going to compute plate height, okay? So we measure those three things, we know those three things, and for any peak in our chromatogram, I can compute H. Remember, minimizing H, making it as small as possible, is what we want to do, okay? Make it as small as possible. Smaller plate heights are better than larger plate heights. So last time, I think the video that we talked about, with this multiple flow paths business, this longitudinal diffusion, this is of course that Van Diepter equation that we just developed last time. You're basically adding together these effects, and that basically gives you an idea what that plate height is, okay? So the Van Diepter analysis again is basically where you plot your H versus your linear flow velocity. And remember what happens is it goes through a minimum and then comes back up again. And that minimum right there is our best conditions for chromatography for the peak under study. That flow velocity, that is the flow velocity or flow rate of our mobile phase that we want to use to achieve the best chromatography possible. And again, we're balancing all these factors down here, okay? All right, so that's computing plate height. Now there's a couple more variables that I want to talk about in this video. There is another term that chromatographers use to discuss chromatographic performance. And this is the number of theoretical plates, which is given the symbol N, capital N. So plate height is big H, number of theoretical plates is capital N. And this is just another way that the people can express performance in chromatographic behavior. Now, the formula for N is quite simple to H. We actually need to know the same three variables. So if we go to look at our chromatogram, we see our Gaussian shape plate peak. Remember, this is detector signal in time. Okay, T sub R is again just that retention time. That goes into the numerator. W is still the width at the peak base. That goes into the denominator. Take the ratio, multiply it by 16. That is your number of theoretical plates. Now for N, the number of theoretical plates, larger values are better. Better chromatographic performance for larger values. And that makes a lot of sense, right? Because if you look at the form of the equation, it's the retention time over the width squared. I mean, that's kind of the nuts and bolts. You got to multiply by 16, right? But that's the nuts and the bolts of this, right? Now, if your retention time is big, it takes a long time for the peak to get to the detector, but your peak is very, very narrow. So you have a nice skinny chromatographic peak. That's like best case scenario. Width is very narrow, retention time is large. That's best case scenario for chromatography. Now why is that? Why is that considered good, right? Having these tall, skinny peaks. Why is that considered good? Well, it's considered good because in that separation, if you have tall, skinny peaks, you're confining all of your analyte to a very narrow range in your column. And basically what that means is if you have another analyte in your sample that elutes right here, well, you have a distance between these. You can separate them and you can measure each one individually. Now, if your peaks are much wider, like up top, and you have another analyte, and maybe its elution behavior is like this. Okay. Now there, have you achieved full separation of the zones? No, you haven't, have you? This region in through here is a mixture. Once those peaks reach the detector, they're going to be a mixture. And if you were to collect into fractions, you'd actually still have a mixture of these two substances. So tall, skinny peaks are better because it allows you to fit more peaks into a given chromatogram, okay? The last chromatographic term I'm going to tell you about is resolution, peak resolution. Now, to this point, we've only been talking about our chromatographic performance in terms of one peak, how narrow it is compared to its retention time, basically. Resolution goes beyond that because what resolution does is it compares separation two peaks instead of just one. So let's consider. Well, first off, resolution is something that we're going to compute. It's given the symbol R sub S. And the way we're going to compute it is we're going to do T2 minus T1. And in reality, that should be TR2 minus TR1. I guess I feel better about that terminology. Divided by 1/2 W1 plus W2. And it doesn't matter the order, 1 and 2 in the denominator. So this is our resolution, peak resolution. Okay, now what does that mean? Well, in our chromatogram, if we're going to compute resolution, you are going to have more than one peak, maybe something that looks like this, okay? This is your time axis, signals the other axis, right? So you have not one, but two peaks. So we're going to number them peak 1 and peak 2, respectively. So what this equation tells us to do is you're going to figure out your retention time for peak 1 and your retention time for peak 2. Okay, remember that's the time it takes to reach the detector. This is TR2. And that's TR1, retention times. They have different retention times. They're not the same substance, okay? You also need to find your widths. And we're going to do that at the baseline. Down here, the peak at the base, the width of the peak at the base. It's W1 and W2, respectively, right? We're going to measure W1, W2. We want to plug those in here. And we're going to plug in our retention times in the numerator. And it's really as simple as that to compute the resolution. Okay? Now, if I was to kind of think about this equation for a second, what it's actually showing me or telling me, what it's actually saying is to take the difference between the retention times and then divide by the average peak width. So if the difference between the retention times, let's say these peaks have similar widths, okay? If this delta TR, the difference between retention times, is greater than the average width, we'll have a resolution above 1. And this is really what's desired. Even a resolution above 1.2, 1.3. And if we can achieve that, we say our peaks are baseline resolved, which means that our detector signal returned down to baseline before the second peak began. It's baseline resolved. in terms of resolution, you're going to have to be up over 1 for that to be achieved, for that baseline resolution to be achieved, okay? So resolution provides a metric where we can basically describe to others our efficiency of separation with separating two particular substances in our chromatogram or comparing two peaks, okay? That's how you compute it. And I think that's our last term that I'm going to tell you about in terms of chromatographic performance. I'm going to end the video here, and then we're going to start talking about instrumental apparatus for GC and LC, which will be a lot of fun.